Okay, hello everyone. We are a group that did the research on the biodiversity and climate relationship. I'm Fred, Dongyang.
I'm Dongyang.
And Spencer.
So for the introduction, climate change and air quality are both critical environmental factors that significantly influence the health and sustainability of ecosystems. According to previous research, air pollution can have a number of negative effects on plant diversity, insect populations, avian, fish, and mammal diversity, and microbiome communities. Air pollution can have direct and indirect effects on biodiversity, and these effects can be significant. It's most important for us to explore and predict the relationship between air quality and biodiversity to avoid future abuse of nature and better protect our environment. So based on our introduction, our research question is that can the effects of climate change and features from national parks predict biodiversity? Existing research has found that parks with higher biodiversity tend to show greater resilience to climate change, showing a relationship through which we can construct the model. And our results complement existing assessments of climate change vulnerability in U.S. national parks by reviewing the issue from the top down across all national parks, whereas other studies typically only review case studies at individual parks or in locations other than national parks.
Okay, for the description of data for the biodiversity and annual AQI, the data longevity of the biodiversity data is the decades of observation and reporting, and AQI data is from the 2016 data for every county in the United States. And granularity for each dataset, the biodiversity dataset shows the species information that live in different national parks, and the AQI shows the air quality summary for individual counties across the US. And the following is the EDA results. This is a percentage of noun values and the number of unique creatures in each state. This is a unique number of unique creatures for each order and the percentage of national parks categories. For methodology for those two datasets, first we compile the AQI data into the biodiversity dataset and then group by national parks to avoid meaningless duplication of data. And we use the linear regression model as the predicting model to train the datasets and choose the RMSE as our error function. And then we use the cross-validation to choose the appropriate model. And finally, we use the gradient descent to see the optimal coefficients to minimize the error. The result for the biodiversity and AQI datasets modeling for the cross-validation error results is the error from the model using the number of species is larger than the error from the model using the square roots of the species. So we built a linear regression model based on the square roots of the number of species and using the features, the square of the 90th percentile AQI, number of orders, number of families, number of occurrences listed as presence, and the latitude. The RMC of this model is around 3 to 4 for the test dataset size of 12. For the gradient descent, we can see that the optimized coefficient for each feature and their actual impact on the prediction model.
All right, and for air quality data, this is from a period of 5 years, hourly granularity, which we average to weekly, metrics including various features of air quality and climate, including temperature. There are many null values because it was very decentralized, and we use log transformation to normalize the distributions and make the data more interpretable. These are the distributions, part of the EDA. You can see that there is a bimodal distribution in several of these, with a peak later on along the x-axis. And this is the annual violin plots showing the distribution of values. As can be seen for these three features, there is, again, bimodal distribution with the upper mode trending upward, indicating climate change. These are two covariance heat maps. One thing for the larger heat map is the correlation between PM 2.5 and temperature, which would indicate wildfires in the area. The nature of the data set for the air quality analysis was very multidimensional, with parks and the specific features collected from those parks, and then the specific hours they were collected on, and the biodiversity data for each individual park being a static piece of data made it very complicated to simplify it down into something that can actually be analyzed. So we did that by constructing a linear regression. After merging all these together and preparing the data sets, we did a linear regression to construct the time series coefficients for each park's feature, and then did another linear regression on those coefficients according to the biodiversity metrics to get a sense of the predictions for future trends in climate change based on those biodiversity features. This is what that looks like there. So positive indicates less resilience to climate change, negative indicates greater resilience to climate change. So spiders and scorpions being in the national park are associated with greater impacts to climate change. And then fish, birds, non-vascular plants, and mammals exhibit greater resilience to climate change impacts for being in those areas. There is a much greater impact of climate change on areas with proposed threatened species, whereas endangered species and in recovery species show a greater resilience to climate change, which possibly indicates the intervention of humans and preservation efforts. Surprisingly, the abundance of non-native species, otherwise known as invasive species, is indicated with a greater amount of resiliency towards climate change, which might be, which is a confusing result, but that is what we got.
For discussion of the biodiversity and AQI datasets, we found that the biodiversity dataset was limited because it was simply an aggregation of unrelated ecological surveys over multiple decades, rather than a progression over time like the air quality datasets. Despite the limitation of data, we were able to find some interesting things. The first is the residual plots for the linear regression model was generally random, which indicates that the model does not have a very strong bias. The cross-validation error was significantly reduced by square rooting the number of creatures. And this suggests that this model is more accurate when it is applied to a larger dataset.
And nothing new there's nothing new on the slide that I haven't already mentioned before. The abundance of species that were not native to the particular national park was correlated with greater resilience, whereas the number of proposed species proposed as threatened is correlated with a greater impact of climate change, less resilience, possibly indicating the need for intervention from humans to improve resilience to climate change. And for future research, addressing the things that we've already mentioned, getting a time series data set for biodiversity and allowing more flexibility for the analyses, making it easier to find and predict these relationships, extending the time series period beyond 5 years to get more variation in the model to allow for greater, more accurate predictions, and then incorporate other dimensions of biodiversity and of air quality and climate in the future. Then also examining the impact of formal species status indicators for climate resiliency and the effect of human intervention of preservation efforts in improving climate resiliency for those indicated as in need of preservation, and then standardizing the air quality and climate data collected by individual parks to cut down on the amount of null values that are being collected. Thanks. That's the end of our presentation.